Hello and welcome to another video lecture in Math 442. Now I'm going to start talking about Chapter 8, that's Stiff ODEs, and I'll explain what that means in a minute. I'm probably going to do a few Matlab demonstrations, so this may be a little bumpy. Hang on and let's get started. Chapter 8 covers stiff ODEs, and let's start with the definition of that. We call a problem stiff if we're trying to compute a particular solution that it's a smooth function, so it is nice and differentiable. It's slowly varying relative to the time interval that we're computing, but there are nearby solution curves that vary much more rapidly than that solution. And I'm going to start by really just going through the examples in your textbook. So we have looked at this particular example before because it was a nice example of how we can see some instabilities in our basic solvers if we use an ODE like this and throw some solvers at it with too big of a time step. So now we're going to talk about it in a little more general detail and motivate some other ideas of stability. If you recall from equation 7.2, this ODE has the solution cosine t, and just put this little initial condition with it for now, okay? This is what we refer to from above as the slowly varying solution, cosine t. Now, that is actually the solution no matter what value of lambda I choose. And you can see that if you read through the rest of the notes and read through the textbook a little bit. But now let's think about perturbing this data a little bit. So now let's pose exactly the same ODE with some data where this eta value is close to 1, but it's not exactly 1. And the T0 value is close to 0, but it's not exactly 0. If you solve this equation more generally, and you may recall, you can do this via Duhamel's principle from chapter 5. You did this on a homework assignment. You can write down a nice form for this, which has lambda floating around in the parameters. So here's me just applying that Duhamel's principle, and here's what you come up with, okay? There's some integration to do, and I won't go through any of that. I'll just say this is the solution of that initial value problem for any choice of T0 and eta like we saw earlier. So now what I want to do is focus on a particular case. All right, so if lambda is negative, u of t, it approaches cosine t as t increases, okay? And you can kind of see that if you just look at the algebra here. Lambda being negative means that this guy, well, this term is going to 0 as t gets larger, as t moves away from t0. And lambda is negative. And so this entire term that you see here, let me do this. This entire term is sort of what we call transient. It's short-lived. So that term is going to be made small the further that t moves away from t0. What this means is that overall, this entire solution u of t is going to approach cosine t very quickly, actually exponentially quickly with decay rate lambda, or we say sometimes, we say that this term vanishes very quickly so that only the u of t equals cosine t is left over. I'm going to show you some demos, and I'm not going to use dfield here. I'm going to use a GeoGebra application. So I'm going to stop sharing and change gears. If you have D field running properly with your Matlab installation, you're welcome to use it. If not, you're welcome to follow along with the GeoGebra applet. It's all you need is a web page, and you can crank it in really quickly. And so I'll show you in just a jiffy. All right, so let me show you some of the GeoGebra version of the direction field so I can explain the details of this example. As you'll see here, if you follow the link that's on D2L, you can find this little applet online. And when you first show up at the page, it's going to look like this. So we have to do a little bit of adjusting, and we have to use their language. So Y and X here instead of Y and T. Don't forget to put parentheses around the, the sine and the cosine, or the X inside the sine and the cosine. Now, what you're looking at here, let's see if I can maximize this. What you're looking at here is the full screen version of this example. And now here is the direction field. Right now, my lambda is -1. And to play with this, what you really have to do is you have to click on this little red dot and move it around. So that's like prescribing your initial condition to this plotter. So notice as I moved close to X equals 0, and I can't get right on it, but when X is equal to 0 and Y is close to 1, you can see the cosine function really showing up, right? And so here is that cosine function, cosine T or cosine X in terms of this, this expression. And you can see how it's a nice slowly varying function. But now, if you take your mouse and you click and hold on this little red dot and start to drag it around, notice what happens. I move just off of it. So I perturb that initial condition a little bit, either this way or this way, left and right, or maybe up and down. And I see that what's really going on here is as T gets further away from, say, T equals 0, in this case, I'm still really paying attention to cosine X. The solution is really converging, if you might say, as X increases to just the cosine X term. But notice for negative X, or X is away from my little red dot here, it's away from the cosine X, and that is due to that exponential contribution to the algebraic expression for the solution that I showed you earlier. So play around with this, and you can kind of think about right now what the slopes of these lines look like. And here's what I'm going to do. Just like your textbook, I'm going to go back over here, think about what that looks like, and now I'm going to change lambda from a -1 to a -10 and replot. And as you can see, I still have this very slowly varying cosine function, which is the true solution. However, as I am moving this guy around, as I move it left or right, or I even move it sort of up or down, I can see that part of the solution, this part, the part before you get to T equals 0 or T equals T naught, in this case, T naught is equal to 0. There is a very quickly varying portion of the solution, which is, of course, denoted by very steep little tangent lines here, because that's what this direction field is. It's just a plot of all of the tangent lines to the solution curve. And as we get close to this underlying cosine x curve, those tangent lines look more and more like they should for cosine x. And when I am away from that curve, all of a sudden they're extremely steep. They're either very negative or they're very positive. And now let's go back and think about a little bit more what this means in terms of the algebra. So let's go back to the notes. I have reproduced the graphs that you will see in figure 8.1 if you're reading through this example in your textbook. And I have basically showed you exactly what this remark says right here. So now what I'm going to do is start thinking about a slightly different example. That is the chemical kinetics example. This will be the same chemical kinetics example that you saw earlier in the previous chapter, and I have some Matlab code to show you on that. Now I'm going to show you some Matlab examples for that chemical kinetics problem. So let me share my screen again. You should be seeing my entire screen so that I can flip back and forth between an M file and this command window. Now what you should be seeing is an M file, which is the chemical kinetics version of ODE sample.m. So this is actually example 8.2 in your textbook. I've modified that original M file so that now it runs this example, and it does everything that the original M file did before, only for a different system. And I'm going to run it for a couple different cases. I'm going to run it for the original. And this is exactly set up for that example to generate those figures. And to start with, we are going to run just a simple case. So we're not going to run the ODE sample test. We're just going to run ODE sample for a specific tolerance, so you can see. There it is. Now, hopefully you can see that what got generated was a figure file. And you saw this before, chemical A, B, and C. They have a time profile. Now what I'm going to do is go back and edit this M file so that now I put it in a different figure. And I inject a little extra chemical at a certain time. Oops, just like your book describes. And I want you to check out the difference. Okay, so I have two figures here. Figure 2, and you can see where that injection happens, and you can see the reaction to that. Oops, wrong figure. And now I want to take a look at these side by side. Now, our previous example showed that there's some little change of nearby solutions, but everything goes back to that cosine t term. This one is not exactly like that. Now I insert from this, if you want to call it the nominal solution, I insert a little extra chemical at a certain time, say t equals 1 here. What happens is that now that extra addition of chemical changes the actual equilibrium value here, because now I don't have 9 units of chemical, I have 10 as a function of time. So this means you're not necessarily going back towards that same function that you were trying to find before. You've now gotten on to another solution profile. Now I'm going to stop sharing for just a minute. So what you see here is two different kinds of examples of stiff systems or stiff equations, stiff system of ODEs. In the next video, I'll say a little bit more about what this actually means or what the consequences are for that. Thank you.